is the Kmeans algorithm, and we'll talk about it in detail, and then we'll go into other forms of clustering algorithm. Okay, so K-means is a partitional clustering algorithm. I'll talk about what is partitional clustering. Well, as the name suggests, it partition the data into different cluster. Okay, so it's just an example. Let there be a set of data points. Okay, and let's say there are x1 to xn. So there are n number of data points. Okay, so what the K-means algorithm does is that it partitions the given data into k cluster. Okay, so n number of data points have been clustered into k clusters. A k is a real number, it cannot be a fraction or a negative number, right? K could be 2, or could be 4, could be 8, or 9. I mean, it could be any number, right? And each cluster should have a cluster center. We call that as centroid. That means that's the center of the cluster, and k is being specified by the user. Now this is very important, that you only, if you perform k-means clustering, you are the one who is going to provide how many clusters are there or are present in the data. That happens to be one of the weakness of this algorithm. But if you're working in that data for a while, and let's say you are a marketing manager and you're working on a marketing data, then you know how many clusters are there in your data, but you do not know which data point belongs to which cluster. So K-means algorithm basically helps us knowing which data point belongs to which cluster, but it doesn't quite help to know how many clusters are there in general. That has to come from yourself. Okay, so how does this algorithm works? Well, it works in 4 steps. So in the first step, it randomly chooses k data points to be the initial centroid of the clusters. Okay, let's take an example. So let's say we have a set of points. Okay, so it randomly chooses, let's say we say that we know that k is 2. So there are 2 centroids. So here is one centroid, this data point is one centroid, and this data point is one, which we have chosen this randomly without being biased. Okay, in the second step, assign each data point to the closest centroid. That means here is a centroid and here is another centroid. Just calculate the distance uh, and then see which data points are closer. Now you can see, and these data points are closer to the first centroid, these data points are closer to the second centroid. Okay, now you recompute the centroid after having the cluster. Now you have two cluster, cluster 1 and cluster 2. You recompute the centroid, and centroid can be computed by by taking average distance, right? So some other data point could be now a centroid. Then the second step, maybe another data point became a centroid, and then you group the data points in different cluster. You keep repeating, okay, till the time there is no convergence. And what is the convergence criteria? In the next slide we'll talk about. Next few slides we have what's the convergence criteria. How do we know that the algorithm has converged? Okay, so that essentially is the way. So the way we know a convergence criteria is to see whether there is no reassignment of data points to different clusters. That means you do the iterations, right? I talked about the iterations, that in the first iteration you yourself, I mean the algorithm will randomly choose the centroid, but the next step it will calculate centroid based on the existing cluster. Okay, and in iterate, keep on iterating, right? There will be a time when there is no reassignment the first time. So I'll show you an example in the next slide, and that will be way but more clear. Well, there will be reassignment data points to different cluster in every iteration, but there will be a point where there is no reassignment. It's no changing. In the next iteration, it's the same as the previous, and that's when we realize that we have reached the convergence. Uh, and there is no minimum change in the centroid. That means the error term, the distance of each point from the centroid, is remaining constant in each iteration. It will obviously go down with iterations, but there will be a point when this is not going to change. So these are some of the convergence criteria that the algorithm uses. Here's an example. So we have set of data points. This is the first step, and we put through this clustering K-means algorithm. K-means algorithm chooses two data point, random data point to the centroid, and accordingly it assigns data points to different clusters. So here is one data point, and second one is this one. So these are two data points chosen randomly, and remember, randomly. That means you haven't provided. You only have provided that k equal to 2. That means there are only two clusters present. So there are two centroid. Now it calculates the distance and finds out that these many data points are in these, in this cluster where centroid is this one. These are the data points which should be in another cluster. Now you recompute the centroid. That means now you don't have to do it randomly. The first time you did it randomly, right? Or the algorithm did it randomly. The second time it has to calculate the centroid by taking the distance of each point, and centroid is nothing but central point of a cluster, right? So this will be somewhere here. So here also this will be somewhere here. The centroid will be somewhere here because this seems to be the central point of the cluster. Okay, so just by calculating the distance of each data point within a cluster and taking an average, you'll be able to find out where exactly you end up having your centroid. Okay, so one of these data point will be again a centroid. Now this centroid has changed, right? So in the next step, in the next iteration, in the second iteration, you can see centroid is here and here. Previously we had here and let's say here, right? So this has changed now. So centroid has changed. If centroid has changed, the next step would be that you again calculate the distance and regroup the clusters. That means the nearby points will be in the nearest cluster. So this cluster, this data point is very close, but this is far off, right? So this data point should be in this cluster, not this cluster, right? So this regrouping will happen in the next iterations, and that's what it is. You can see, right? So the data point, so this data point I showed you, right? These two data points are part of this cluster, and these data points are part of another cluster, and that's what you can see here, right? There's a clear difference in the last iteration and this iteration. Okay, in the next step, you can see there's a clear difference. Then again the centroid will be calculated, and there isn't much change. Centroid is somewhere here, centroid is again somewhere here. Then you calculate the distance of each point and try to regroup the data points in a cluster, right? So each data point is closer to this one, so this is one cluster. These data points are closer to this one, so this is another cluster. But you see that there is no change. This is exactly the what we had in the previous step, and you continue for a few more times. You see there is no change after that. After the first iteration, there is no change. That means we know that the algorithm has now converged, and we now finally have two clusters in place. Okay, so this is the way the algorithm works. That it works with iterations where there is a recomputation of centroid and reassignment of data points to different clusters, and only when there is no change in few iterations, then we assure that there is no change. How do we calculate the distance is a very important questions to ask. Well, we all know about the Euclidean distance, that given as two different points, let's say x1 y1 and x2 y2, you can calculate the distance by taking the distance formula, like which is x2 minus x1 square plus y2 minus y1 square, and take this square root of that, and that's your distance, right? So that's the way we calculate. So this is the distance formula, and you can calculate. This can be generalized also. Okay. Okay, there's some. So we talked about the theory of Kmeans, and hopefully this is somewhat clear, and we'll see how we can perform using the software. So I have written R code, and I'm going to show you. So what are the strength of Kmeans? Well, Kmeans is very simple. It's easy to understand. As you can see, it's very easy to understand and very easy to implement, and it's also very efficient. It's the linear. That means when you have large data set, the performance is quite important. Many times, uh, the algorithm can take a lot of time. Many other algorithm can take a lot of time. So this is, since this is linear, this is much better when you have large dimension. Hence, it's very popular. But there are some weaknesses as well. The algorithm is only applicable if the mean is defined, and many times your mean wouldn't be defined, especially when you do not have the numeric data. In that case, you won't have a mean, right? So k-means is not applicable in those cases. The user needs to specify k. So you have to be an expert in the data that you are working on. That means you should know how many clusters are there in your data. You cannot afford to have this from your algorithm. The clustering algorithm will not tell you how many clusters are there in your data. You just have to provide whether it's k2 or 3 or 5 or 6, whatever. The algorithm is very sensitive to outliers. That means when you have extreme observations or observations which are very different from rest of the observations, then are very far away from other data points, then the algorithm doesn't perform well. We'll take an example to show you how that affects. So here is a typical examples of k-means algorithm not doing well when you have an outlier. So here you can see you have set of data points and we have another set of data points. Okay. Now, if you use k-means clustering algorithm in this case, it and k equal to 2, let's say, it combines these many data points to be cluster 1 and the other data point set of data points to be cluster 2. But ideally, this is not a good clustering because one of the data point and this one is far away from the other data point. So that data point should have been removed, and then we would have got a much better clustering segment. Here in the second graph you can see if you remove this data point and build two cluster, you can see a much more clearer clustering, a much more elegant, much more clearer, right? If you just remove that, right? But here you can see these data points have been clubbed with this data point, which is they are very far away, but yet they are in the same cluster. That doesn't make much of a sense when you try to interpret. So it's very sensitive to outliers. So you should deal with outliers before using clustering. There are methods to deal with outliers. So one method is to remove some of the data points in clustering process that are much farther away from the centroid. That means just remove them, right? The way we did, we just simply remove them. We simply did not use this data point, and then the clustering is much better now. So that's one way. The second way is to take a random sampling. When you take a random sample, then you will likely to not include many outliers in your sample. Okay, so that's the second way of handling outliers. The algorithm is very sensitive to initial state. That's another weakness of k-means. Okay, so initial state means when you first or the algorithm rather first chooses the initial points, that will decide how the clustering will happen. Okay, here is a typical example. We have taken the same example, right? So this is one cluster, this is another cluster. But let's, for instance, the initial data points have been chosen to be somewhere here and somewhere here. Sorry, somewhere here. The first one, the other one would be somewhere here, not this one. So in that case, the first cluster will be this one. It will take half of the first one, half of the second one, and you combine it as a one. In the second time also, then you recalculate the centroid, and the centroid comes out to be here, and then it doesn't change. Now you can see this is not a proper clustering. You are getting somewhat of a misleading clustering. Should have been like this one, right? This set of clusters and this set of clusters. So you can see not very clear clustering happening because the initial seed or the data point that was selected wasn't a very appropriate one. So that's a typical issue. This is a much better cluster segments than the other one that we just saw previously. Another important weakness of k-means clustering is that It's not very good unless you have hyper ellipsoid cluster segments. For instance, if you can see this one, there is two clear clusters, right? So this one is the cluster and the other one is this one. Very complicated, very non-linear form of clustering, but there's a clear cluster, clearly the two different clusters, right? But what it does is that it takes the upper half as one cluster, it takes the lower half of the second cluster. It's not, which is not proper, right? It is not a correct representation. So this is, unless you have a very um, clear shape of your data, then the clustering will be somewhat not appropriate. So here's an R code for doing K-means clustering. So you can in fact take this data and you can run it on your own. So iris data is what I have taken. Iris data is available on R. You can just use it. You don't have to import it from anywhere. So iris data has got the data for flowers. There are three different categories of flowers, and then their petal length, then petal width, sepal length, and sepal width. Okay, so these four attributes of the flowers have been given, and then using K-means clustering, we are trying to see whether we have these three segments of flowers or not, and then we'll try to see if the actual segments for three different types of flower is similar to what the clustering algorithm has given us. Okay, and then we'll do a comparison. Okay, you can run it on your own. So here is a code. So we use K-means function, and we have taken four attributes from the iris data to do this. You can run this, and then you can validate using the actual clusters and the predicted cluster, and to see uh, how well this algorithm does. You can take it this code to the R and run it by